So this chapter is going to be about significance test. So significance test is the procedure that we use for taking observed data and using that to decide between two hypotheses. Those of y'all that have taken AP biology before, we've talked about a null hypothesis versus an alternative hypothesis. So we're going to be learning a number of different kinds of significance tests to decide between those two claims. So the first thing we need to do is be able to state those two claims. We have to be able to state a hypothesis, and we need to be able to do that well. So the first kind of hypothesis that we're going to have is what we call a null hypothesis. Okay, this one is represented there by the H naught. Okay, and so this is the claim that we're weighing our evidence against. Okay, a lot of times it's a statement of no difference. When we would use this in biology, we would talk a lot about saying that our variable had no effect. Okay, and so, or in that would be the same as it having no difference. Okay, this is what we're trying to look for evidence against the null hypothesis. Okay, because as a general rule, we're doing some kind of experiment and we want it to go another way. We want it to make a difference. Okay, so we're looking for evidence against this one. One of the ways that you can remember how to write this is keep in mind that this is your dull hypothesis. Okay, it's your boring hypothesis. Nothing is happening. There's no difference. When we're talking about statistical things, this could be, a proportion or a mean. We're going to talk a lot about a basketball example. And in this basketball example, the claim is the basketball player claims that he makes 80% of his free throws. Okay, so again, the basketball player claims that he makes 80% of his free throws. So the null hypothesis for that particular scenario would be the probability that he's going to make his free throws equals 0.8. Okay? There's no difference from what he claims it to be. Whereas our alternative hypothesis, this is what we think of, this is kind of more your typical hypothesis that you would make in science. Okay? So your alternative hypothesis, this is the claim that we suspect is true. We think that he probably doesn't make 80% of his free throws. That's pretty high. Okay? Or maybe you're doing a particular science experiment and you think whatever your variable is that you have is going to have an effect. So this is what we hope or suspect is going to be true. Okay? In our basketball example, our alternative hypothesis would most likely be that the probability is less than 0.8. Okay, that he doesn't make, that's a false claim, that he's exaggerating and he doesn't make 80% of his free throws. For this one, we are trying to find evidence that supports it. Okay, so we're looking for evidence that is for our alternative hypothesis. Okay, so let's look at an example and practice writing these. So we have an example here about pineapples. So the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in the field after the growing season. Managers wonder how this change will affect the mean weight of pineapples grown in the field this year. So our problem here is we're supposed to be stating appropriate hypotheses for performing a significance test. Be sure to define our parameter of interest. Well, our parameter of interest, hopefully we've gotten pretty good at that at this point, and as long as we're using it in context. So our parameter of interest here is going to be our mean weight, mu, of all the pineapples grown in this field in this year. So the mean weight mu of all the pineapples in this particular field this year. We can't draw conclusions anywhere other than that. So that's my parameter of interest for this. So my hypotheses for this, I'm going to need a null hypothesis and I'm going to need a alternative hypothesis. Well, remember, my null hypothesis is my dull one. There's no difference here. So my null hypothesis would be that the mean weight is the same as it was before, that it's not any different, that the mean weight here would be 31 ounces. Where my alternative hypothesis is going to be a different hypothesis, And when we're looking at this scenario in this problem, it didn't say anything about the mean weight of the pineapples being less than, or if the mean weight of the pineapples was more than. Okay? We're really just looking to see if the mean weight of the pineapples is different. So if the mean weight of the pineapples is different, it could be less than or it could be more than. So in this scenario, my alternative hypothesis is going to be that the mean weight does not equal 31 ounces. Different than the basketball one. So in the basketball one previously, we said that the alternative hypothesis was that he shot less than 80% of his free throws. And these two ways that you can write this are what are called a one-sided alternative hypothesis. I don't know what happened to my arrow there. Versus a two-sided alternative hypothesis. So a one-sided hypothesis, okay, is going to be like it was with the basketball. So this is our basketball example. Okay, it's either larger or it's smaller. Basically, we picked a particular direction that it's going to go. Where our two-sided one is just the fact that it's different. So this would be the pineapple one. We're not looking for it to we're not looking for those pineapples to be bigger or them to be smaller. We just want to know if they are different. So a few more tips when you're writing these alternative hypotheses, okay, is that your alternative hypothesis is always going to be that the parameter, so for instance, that's why we defined our parameter on the pineapple one. So in the parameter, for the pineapple one, it was the mean weight of the pineapples. For the basketball, it was the proportion of free throws that he makes. But it's always going to be the parameters greater than, less than, or not equal to the value. Okay, the 31 ounces from the mean from the previous year, the 80% that the basketball is claiming that he makes. Okay, your null hypothesis, when you write that one, okay, your null hypothesis is always going to be that the parameter equals the value. So you have three choices for alternative. Okay, right? These two would make it one-sided if you used one of those. If you use the do not equals, that makes it a two-sided alternative hypothesis. Okay? When you are writing these hypotheses, keep in mind that you are always referring to the population. Okay? Always referring to the population, never to the sample. So when you're writing when you're writing hypotheses, you're always going to use the population parameters, never using the sample parameters. Okay, always use the parameters from the population. So, for example, where this becomes a key is with your notation. Okay, so for a hypothesis, you would use mu. Okay, you would not use x, because remember this is my sample, where mu is my population. So just keep your notation, right? I would use p for proportion. I would make sure that I am not using p hat. Okay, so just make sure that you're paying attention to your notation for these. Okay, so why do we do a significance test? So the point of these tests are to help us determine if we got significant data for the alternative hypothesis and against the null hypothesis. Remember, we're looking for data against the null hypothesis, and we're looking for data that supports our alternative hypothesis. So this significance test is going to help us answer how likely we were to get the results from the particular sample by chance when the null hypothesis is true. So again, this is going to answer how likely we are to get the result of the sample. So the result is the sample. To get that particular result by chance, given that the null hypothesis is true. Okay, so let's kind of put this into play here. So let's look at the basketball one again. Okay, so in the basketball one, remember our claim, right, our null hypothesis here was that he makes 80% of his free throws. Okay, well, we did a sample, And we did a Fathom. So what you have here is the Fathom software, and this is a dot plot of free throws. Okay, so 50 shots, and there are 400 sets. Okay, so let's say we have this basketball player, and this basketball player takes 50 shots, and he makes 32 out of 50 of those shots, which means our particular sample for this, our p hat here, is 0.64. 0.64 is kind of far off from 0.8, okay? But is it strong enough evidence to say that the 0.8 is wrong, okay? That we would reject that null hypothesis. So if you look at your simulation data there, we've got 400 samples taken here, okay, based on using the software. Okay, and if we look, they've got them circled right here for you. Okay, if you look at them, we've got 3 of them where he made 0.64 or even less. Okay, so where he made 0.64 or even less, which means that becomes, let me get rid of this writing over here. So that becomes, remember our p hat was 0.64 for the sample, right? Okay, and so this is 3 out of 400. So basically, I get a probability that he is going to make, if that claim is true, remember this is all based on if the null hypothesis is true. So if the null hypothesis is true, and so that is the true proportion of free throws that he makes. If the null hypothesis is true, when I run 400 samples of this, I have 3 or less. I have 3 of them where he's making 0.64 or less. So the probability of that happening if the null hypothesis is true is only 0.0075. Okay? That's not very high probability. Okay? So what this would mean is that this statistic of 0.64 is so unlikely, it has a probability of 0.0075, so unlikely if our true proportion was 0.8, then it gives us convincing evidence that this claim is false. So again, what this tells us is that our statistic of 0.64, our p hat, is so that's from our sample, is so unlikely, a probability of only 0.0075, if the true proportion was 0.8, that gives us convincing enough evidence that the player's claim is false. The likelihood of that happening by chance is so low that that gives us enough evidence to convince us that the player's claim is false and that we would reject the null hypothesis. Basically, what this means is that we've got 2 explanations for that statistic, for that kind of weirdo statistic. So our 2 explanations would be that the null hypothesis is correct, so he's true in his claim that he makes 80% of his free throws, okay, and it's just by chance that he didn't, that he had this other event happen, this unlikely event occur. The other option is that our alternative hypothesis is correct. And if that is the case, then that means that the population proportion is less than 0.8, and this was not an unlikely event. So what that would mean is that my population proportion is less than 0.8. My alternative hypothesis is correct. So my population proportion is less than 0.8. Okay? Therefore, then that's going to give me, that's going to make me believe that this was not an unlikely event. Okay? And this is not an unlikely event. And we have to decide basically how much, how much wiggle room we're okay with. How unlikely is unlikely. So these are our 2 options here. The null hypothesis was correct, and that event occurred by chance, that he got this weirdo sample where he only made 64% of his free throws, or that the alternative hypothesis is correct. The population proportion is less than 0.8, and this is not an unlikely event. And in our case, the probability is so low at 0.0075 that we would say that this is an unlikely event, that this is not an unlikely event, that his claim is incorrect. Okay, let's look at what a p-value is. Because a p-value is going to be a probability, and it's going to help us measure the strength of the evidence that we have that's against that null hypothesis and that's for our alternative hypothesis. So the strength of the evidence that the p-value would help us determine the strength of the evidence that we just saw in the last sample. How strong is that 0.0075? Okay, so your definition here in your book tells you that the probability computed assuming that the null hypothesis is true and that the statistic would take a value as extreme or more extreme. That's where in the last example where we said that there were 3 samples because he hit 0.64 and then had a few other cases where he hit less than 0.64, that would be more extreme. That would be even less. Okay, because in our alternative hypothesis, that's the direction we were going, was less. Okay, and this is our p-value test. And so again, this is going to measure the strength of our evidence against the null hypothesis and for the alternative hypothesis, because that's what we're looking for the two. So it is a probability, okay, and we're going to use that probability to help us determine what we're going to do with that null hypothesis, whether we're going to reject it or we're going to fail to reject it. Okay, so if the p-value is small, so if I have a small p-value, then that is going to give me evidence against the null hypothesis, so that we want to reject that null hypothesis. It says that our observation is unlikely to occur if the null hypothesis is true. So a very small p-value, gives us evidence against the null hypothesis, saying that that sample that we have was unlikely to occur if the null hypothesis is true. Whereas a large p-value, so a large p-value is going to give me evidence, it's going to fail to give me convincing evidence against the null hypothesis. So in this case, it fails to give convincing evidence against the null hypothesis. Do not say that it supports it. Do not say that you support or believe the null hypothesis, and don't ever say that you support or you believe. We don't accept, okay? And we don't use vocabulary that implies that we accept. Okay? We either reject or fail to reject. Okay? So what this means, if I have a large p-value, that fails to give me convincing evidence against my null hypothesis, which says that my observation is likely to occur if the null hypothesis was true. So go back to the basketball example. We had a very small p-value. That 0.0075 was our p-value. We had a very small p-value, which gave evidence against the null hypothesis, meaning that that observation, those samples, were unlikely to occur if the null hypothesis was true, which means we would reject our null hypothesis because it wasn't likely to occur if it was really true that he made 80% of them. If we'd had a really large p-value, then we would fail to reject our null hypothesis. We wouldn't accept that he makes 80% of his free throws. We just wouldn't reject that claim because I didn't have enough convincing evidence to do so. Okay, let's take a look at this example with calcium levels. Pause the video for a second, read the problem, and once you've read the problem, we'll go through it. Okay, so hopefully you've read through and you have an idea of what's going on. They gave you a null hypothesis of a mean of 1,300 milligrams per day of calcium intake, an alternative hypothesis of an average of less than that, so less than 1,300 milligrams per day. You'll notice, remember, our null hypothesis is written with an equal. Our alternative hypothesis is less than, greater than, or not equal to. This would be a one-sided alternative hypothesis because it just is using a less than sign. And you'll notice that we use notation that involve the entire population, not just a particular sample. So the first part is asking us to explain what it would mean for the null hypothesis to be true in this setting. So what that would mean if the null hypothesis was true in this setting, then it would mean that teenagers are getting enough calcium because of our mean. So that it would mean if the null hypothesis were true, then that would mean that the teenagers are fine and they're getting enough calcium because our mean is 1,300 milligrams per day. I'm using all my context, right, of calcium intake in the teens. So this would say that the teenagers are fine, it's not an issue. So part B then is wanting you to take the p-value that it gave you of 0.1404 and interpret that in context. Okay. So what that's going to mean, let's clear some space here. So what that will mean is that there is, remember our p-value is a probability. So there is a 0.1404 probability of getting a sample mean, because remember the p-value is referring to the sample. So of getting a sample mean, of 1,198 milligrams or less, because we remember we're going to the extreme or beyond the extreme, and we're going in the less than direction for our alternative hypothesis. This particular sample got a mean of 1,198, so we would be looking at any samples, the probability of getting any samples that got 1,198 or less, okay, just by chance in an SRS of 20 teens. Because I need to use all my context, and I used an SRS of 20 teens. In an SRS of 20 teens. So again, I've got this probability that's telling me that if I took a sample of 20 teens, okay, the probability that I'm going to get a value of calcium intake that is at 1,198 or less is 14%. That to me sounds kind of high. Okay. So if we're trying to determine if that 14% is kind of high, we're trying to determine if it is statistically significant. This is our symbol. We use alpha for the level of significance that we have chosen. A very common level of significance is 0.05, okay, 5%. Okay, basically the same as kind of similar to being 95% confident. I don't want to say that, and I don't want you guys to say that. Okay, a common alpha level is 0.05. Sometimes we use 0.1, sometimes we use 0.01. It just kind of depends on the situation and what's going on. So when we're determining if something is statistically significant at a particular level alpha, in that case we're determining basically whether we're rejecting the null hypothesis and that there is convincing evidence in favor of the alternative hypothesis. So these are my two options. I can either reject the null hypothesis and tell us that, basically meaning that that sample result was very unlikely to happen by chance. I had a very low p-value. It was unlikely to happen by chance. And so that would assume that that's unlikely to happen by chance, assuming that the null hypothesis is true. And so that would favor our alternative hypothesis. My other option is that I could fail to reject the null hypothesis. Remember, we do not accept or imply that we accept the null hypothesis. We don't say that we accept it. We don't say that we believe it. We don't indicate that the null hypothesis is true. We reject it or we fail to reject it. And if we fail to reject it, we need to tack on that we did not have convincing evidence for the alternative hypothesis. Okay, remember this, when this would correlate with a high p-value. Okay, so if you look over on the side here with our exam tip, our conclusion for a significance test always has 3 parts. Okay, so we're comparing it to comparing the p-value to the stated significance level. So my p-value in the last example was 0.1404, and let's say I wanted my alpha to be 0.05, so I would be explicitly comparing 0.14 to 0.05, 0.14 being greater than 0.05. So that leads me to my decision about the null hypothesis. So I fail to reject it because there is not convincing evidence for the alternative hypothesis that there was less than, that teens were getting less than 1,300 milligrams of calcium. So looking at this sample problem that we have here with the battered batteries, okay, the problem is, what conclusion would you make for each of the following significance levels, and justify your answers. So if you need to, pause it, take a second, read the problem. Okay, and so then now let's see what we've got here. So if we're writing our conclusion for this, okay, our battery example here, in this first case, I've got an alpha here of 0.1. My p-value in my problem is 0.072. So now I need to compare, I need to do my 3 steps of writing my conclusion. I need to compare the p-value and the significance level. I need to make a decision about my null hypothesis, and then I need to make my statement in context of the problem. So if we're writing for the conclusion for this, it would look something along the lines of this. I'm probably not going to have room for this. Okay, because the p-value, and I need to state it, 0.0729 is less than alpha equals 0.10, we're going to reject the null hypothesis of a mean equaling 30. And our statement for our step 3 here would need to be in context then. So what does this mean? Well, this means that we have convincing evidence that the deluxe AAA batteries made by this company last longer than 30 hours. Last longer than 30 hours. So in this instance, our p-value was low, so we reject the null hypothesis, and that's going to tell us then that we have convincing evidence that the deluxe AAA batteries last longer than 30 hours. Okay, remember that what that p-value tells us, right? The p-value tells us the probability of the sample, okay, having the particular value that we found. Okay, so having the mean lifetime of 33.9 hours, the probability of a sample having that mean due to chance is only 0.0729, which does not support then that the null hypothesis is true. So let's look at part B then. So part B has you doing the same thing here for an alpha, this time of 0.05. So we're doing our 3 steps for this as well. So again, for this one, we're going to have our comparison because the p-value, I should have left half of that on there, 0.0729. This time, okay, it is greater than alpha equals 0.05. So this time then we will fail to reject the null hypothesis. Okay, and then I need my supporting statement here. So this time we do not have convincing evidence. So we do not have convincing evidence that those deluxe batteries, that the deluxe AAA batteries last longer than 30 hours on average. Last longer than 30 hours, and then you would need to tack on the on average. I don't have room to do that. But what if we screw this up? What if we reject the null hypothesis when the null hypothesis is true, or we fail to reject it when it is true? So these are called type 1 and type 2 errors. So with a type 1 error, we reject the null hypothesis when it's really true. Okay? With a type 2 error, we fail to reject it when the alternative hypothesis is true. Okay, so if you look at this little kind of summary chart here, this tells us about our population and where we could get our errors from. So remember, we have two choices for our conclusion. We can reject our null hypothesis or we can fail to reject it. If we reject it, however, like for instance with the basketball player one, if we had rejected it, yet it turned out that it really was true that the proportion of free throws he hits, the true proportion is 0.8, then we'd have a type 1 error. Okay? If we fail to reject a null hypothesis, and then the alternative hypothesis actually is true, again, if we were using the basketball error, and we failed to reject the null hypothesis, but because there wasn't convincing evidence to support the alternative hypothesis. However, then it turns out later to be true that the probability that he makes his free throws is less than 0.8. Okay, then we would have a type 2 error. To help you remember these, to have a type 1 error, you must have a small p-value. Because remember, with a type 1 error, you are rejecting your null hypothesis basically when you shouldn't. Okay? And so to have a type 1 error, you're going to have a small p-value. Okay? If you have a type 2 error happens when you fail to reject. Okay, so you'd have a larger p-value there, and you fail to reject that null hypothesis. Okay, and so that's when you could have a type 2 error. You can also remember that a type 1 error is going to be smaller than 2. Okay, so just some tips and tricks to kind of help you sort those two out in your head. Okay, so let's look at this example. Again, pause it for a second and read the scenario and get yourself set up before you start again so that we can go through it. So in this particular example with these potatoes, we've been given a null hypothesis of p is 0.08 and an alternative hypothesis that p is greater than 0.08. And p here is our actual proportion of potatoes that have blemishes. So in this case, we're trying to describe a type 1 and a type 2 error and explain the consequences of each one. So remember, a type 1 error, we have a small p-value. We reject the null hypothesis when it is actually true. So in a type 1 error for this case, they would have sent the potatoes away. They would have rejected the null hypothesis and sent those potatoes away. Basically, if I'm rejecting the null hypothesis, I'm saying that p is greater than 0.08, and so I'm going to send those potatoes away. Okay, so if we're going to put all this in context, right, it would say that the producers find convincing evidence. Okay, so they found convincing evidence. So they found convincing evidence that p is greater than 0.08 because they rejected the null hypothesis, but it's really not. So in reality, the p is actually less than or equal to 0.08. So they rejected their null hypothesis when they shouldn't have, which means they sent the potatoes away. So the consequences, remember, this is a two-part thing. You're describing the type 1 error, and then you're explaining the consequences. So some consequences of this could be loss of revenue because they didn't make potato chips when they could have, loss of time. They're waiting for them to bring another batch back, so they get kind of delayed in the making of these potato chips. So a type 1 error is going to look a little bit, a type 2 error. So a type 2 error, again, a type 2 error is going to be when I fail to reject the null hypothesis when it turns out that the alternative hypothesis actually is true. So basically what this means in this case is that they accept those potatoes when they shouldn't. So basically I've got a proportion of blemishes greater than 0.08, but I said I did not. I had it equal to there or less than. Okay, so basically what this one says is that my producers don't find enough evidence for the alternative hypothesis. So the producers, or they don't find convincing evidence. Let's go with don't find enough. That would work probably best. So the producers don't find enough convincing evidence for that alternative hypothesis. Okay, so they keep the truck. Okay, and so basically what this means is I have a p-value greater than 0.08, and I did not realize it. So again, the second part of this question is my consequences. So my consequences is now that I've made potato chips with these potatoes that have blemishes, and I could have people calling and complaining and being upset about these potatoes that they've decided are ugly and they don't like them. So the last thing that we want to mention here real quick is that our significance level, alpha is going to equal the probability of a type 1 error. Okay, and we can show you all the work to back that up, but that's going to take a really long time. You can see it in your book if you want to look at it in your book, and if you want to look at it in class, we can look at it in class. But basically, it's just, like I said, it's all the background work that proves this, that our significance level of alpha is going to equal our probability of type 1 error. So for instance, if I have an alpha of 0.05, then my probability of having a type 1 error is 0.05. Okay, and so that knowing that can help you determine what alpha level you want to use, because you can take into consideration then what would be the consequences of a type 1 error. Okay, and so do I really want to reduce the chances of type 1 error happening, or am I okay with having a alpha of 0.1, and so my probability of a type 1 error is 10%, and those consequences wouldn't be that big of a deal. Okay, all right, so we'll do more practice with this stuff in class, and really make sure that you're paying attention to vocabulary that you're using.